Okay, great. Good evening, everyone. So today's topic of discussion is regarding VHDL. Okay, how to write a program and what are the different steps in Xilinx to implement your project. So we are going to look at the complete flow which can be done in the Xilinx software, which name is ISE Project Navigator. Okay, on your desktop you may have an icon which looks like this. This is an icon. Okay, ISE design suite. So whenever you want to implement an project based on VHDL, we are going to use ISE Project Navigator, which looks like this. First thing. Next thing, when your software, your ISE stands for Integrated Simulation Environment. Integrated Simulation Environment. So that is your ISE. Here we can write down our complete project which has to follow these kind of steps. First, you have to write down your VHDL program file. VHDL program, which will be saved in a file which has an extension of VHD. This VHDL program, after writing down your program, we need to check for its syntax. We need to check for any grammatical errors. Then we are going to synthesize. We are going to synthesize our VHDL program. What exactly synthesize means? Synthesis is a process of conversion your VHDL VHDL program, converting your VHDL program into its equivalent digital logic. Okay, so after performing the synthesis process, we are going to do we are going to check for its behavior. So we will do behavioral simulation. For this simulation, we need to have a test bench. We have to give the inputs to the VHDL program. This test bench file also have .vhd extension. We are going to perform behavioral simulation. We are going to check whether our designed program is working as expected or not. Okay, once simulation is done, we are going to write down user constraint file, and this file has an extension of UCF. Okay, so now we do have three files. One is our actual logic, where we have written down the actual logic using VHDL program. Next file, the file which has been used to test the behavior of our program, to do the simulation of our program. And the third file is UCF file. Okay, the third file is UCF file. Now, by considering these files, which files? The first one is VHDL program. The second one is UCF file. We are going to combine these two files. So that we will create a programming file. What exactly a programming file means to us? Programming file. this file will be downloaded. This file will be downloaded into our device. Into our device. Which device? Device may be an FPGA or a CPLD. Okay, so probably in your laboratory you may have the kits may have FPGA device or CPLD device. You have to check for their nomenclature, and accordingly we have to generate a programming file. For FPGA devices, the programming file do have an extension of .bit file, whereas for CPLD devices the programming file this programming file has an extension of .jade. Just the way in case of microcontrollers, you had a programming file which is having which was having .hex file. So in case of FPGA, .bit, CPLD, .jade, and using how these files are created, how .bit or .jade file are created using the VHDL program and the UCF file. Okay, this is important task. Okay, let us save this one. Fine. Now what we are going to do, we are going to implement simple one simple program. Okay, so that program will give you understanding of the complete flow. So whenever, let me open the ISC network, ISC project navigator from the scratch. So this was a project navigator splash screen, and after you do have this window, let us click on new project. Okay, now let us give a new project name as half adder. Let us try to have a simple design of half adder. Do you remember that we are writing down HDL program? What do you mean by HDL? HDL refers to hardware description language. Okay, hardware description language. It is HDL. Okay, so we have given a name. Do remember that no spaces are allowed. So that's why you have to take care while giving all the names. This is a device configuration. Okay, this is a device configuration. So you do have lots of things to configure over here. By default, what we have product category, all products. In these products we have chosen a Spartan 3 device, which is a FPGA device. Okay, out of this Spartan 3 family we do have XC3S50. What exactly X sorry XC3S50. Now pay attention. X stands for Xilinx. Okay, C stands for commercial, 3S stands for Spartan 3 family, and this number 50 are the number of CLB components inside FPGA. What is CLB? CLB stands for configurable logic blocks. So the FPGA device do have configurable logic blocks. The logic blocks do have its own architecture where your programming file bits are stored along with the required logic. Okay. So moving on to next, coming back to our project navigator. So file, new project, half adder. Let me put down the things again. Next. So we do have device has XC3S50, then package PQ208. 208 stands for number of pins are 208. Speed is -5 -4. So depending upon the actual device on your kit, you have to choose -5 -4. These numbers are given onto your device. Those are written onto your device. So what exactly speed means? The speed means it is the minimum possible delay. Okay, negative minus sign. Minimum possible delay in terms of nanoseconds between two CLBs. Okay, CLB. CLB stands for configurable logic blocks. So since this gives us information about the minimum possible delay, that too in nanosecond, therefore it is indicated as minus. So -5 refers to 5 nanosecond delay in between two CLBs. You cannot have faster designs than that. You will have at least 5 nanosecond delay from input to output. Rest of the things, do remember that those has to be carefully chosen, and here you have to remember to change your preferred language as VHDL. Pay attention towards preferred language is selected as VHDL and not Verilog. Even if your program is correct, you are going to use the VHDL languages, and if this option is chosen as Verilog, you will fall into lots of syntax errors. So the preferred language is VHDL. Next, this gives us the project summary. Okay, so click on finish. This will create our new project. Okay, the project has a name, half adder. Now right click on this device. Right click on this device. Click on new source. Now we want to create a VHDL module, and VHDL module do have a entity name as a file name as HA. Okay, so we are creating a file for our project and we are going to add it to the project. Click on next. This entity name or file name, okay, is HA. And now since we are doing the half adder thing, we do have half adder which will have input A, which will have input B, and the two outputs, one output is sum and another output is carry. So we are going to put these things over here. So we do have port A, port B, both of them are of input mode. Okay, then we do have port sum which is of out mode. We do have another pin or port which is also of out mode, and all of them are single bit. If input A is a bus or multiple bit, we can put down accordingly. So MSB bit is 3, LSB bit is 0. So this port is of 4 bits: 0th bit, first bit, second bit, and the third bit. But we are doing the simple design, so we will stick to the single bit inputs and single bit outputs. So click on next. This is our summary for the design. Click on finish. This is going to open your VHDL editor. What is this? This is VHDL editor. Let us remove the commented lines. Okay, one moment. Let us remove the commented lines. And let us now discuss about the structure of VHDL program. Now here, if you pay attention, let us make few combinations, few partitions over here. Okay, so we do have upper partition, we have this partition, and we do have another partition. Okay, so the first partition talks about the library and the packages used So over here we have a library whose name is IEEE, and we are going to use IEEE library. Out of this IEEE library, a package whose name is std underscore logic 1164, and all of the definition out of this package. The package name is std underscore logic underscore 1164. This part talks about the entity, or we can say it represents a black box for our design. What exactly entity refers to? Entity gives us information about the various ports. It gives us information about ports or pins required for our design. So let us talk about A, which is written as in std underscore logic. What this means? This means we have a port whose name is A, its mode. Okay, its mode is of in type. Okay, and this input whose name is A has a type of std underscore logic. Okay, std underscore logic. What exactly std underscore logic means? It is standard logic. What do you mean by standard logic? In digital electronics, we had a binary system, logic 0, logic 1. Am I right? It is called as bit logic, but VHDL do not follow bit logic. It follows standard logic. And what exactly a standard logic means to us? The standard logic is a 9 valued logic. Okay, it is a 9 valued logic. What exactly 9 valued logic means to us? In VHDL, we do consider different what I will say that logic values of a signal. So it has uninitialized, uninitialized. A signal may be uninitialized. X, unknown. A signal is present but we are not able to identify it, unknown. We do have logic 0. We do have logic 0. Then we do have logic 1. Then we have Z, which is referred as high impedance. Okay. Next, we do have W. That is, we do have a weak signal, but that weak signal is unknown. We cannot identify it. Okay. Then we do have L. That is weak 0. We do have H. That is weak 1. And the last one is dash. The last one is that dash. This means don't care. When we were learning K-map, the X represented don't care condition, but in VHDL, X represents an unknown logic, whereas dash represents don't care logic. Okay, so therefore, since these all values are practical values, so therefore VHDL is called as 9 valued logic, and therefore we do have std underscore logic represented as a type of the input A and a type of the output, let us say sum and carry. The next part is your architecture. Pay attention over here. Architecture has certain name. Whose architecture? Of the entity name is. We are beginning our architecture and we are ending our architecture. In this part of the architecture, we are going to write down our actual logic for the design. Okay, this whole thing is very structured, and yes, it is easy to understand. Okay, so let us erase all the things and let us type few of the things over here. We are going to implement the half adder logic. Before going to write down, type in the code, let me give you types of VHDL modeling. What this means to us? In what ways we can write down a VHDL program? So we can have a simple behavioral modeling. We do have data flow modeling, and we do have structural modeling. What this represents to? Behavioral modeling refers to write down a simple logic which follows the function table of your design, which follows the function table of design. Whatever is the behavior of design, that behavior is described by the function table, and accordingly you are going to write down your architecture, probably using if, else, then type of sentence constructs, VHDL constructs. Data flow. Wherever we have the logic represented by using Boolean equation, the logic of the design expressed by using Boolean equation, we are going to use data flow. And if we do have large design and we do have different blocks, okay, different blocks inside the structure of design. Here blocks are represented or referred as components of the design. Okay, so whenever we do have components, we are going to use the structural kind of modeling. Here a signal, lots of signal has to be declared. We have to declare the component declaration and component instantiation means declare the component and use the component. What do you mean by instantiation? Use component. We are going to have the connection for those declared components. So these are different types of VHDL modeling. Behavioral is implemented using the function table of the design. Usually we use if else then statements along with the case statements or with select statements. Then data flow, yes, we are going to use Boolean equation to model our design, and a structural, we are going to use the components along with the signals to be which are used to connect the different components. Okay, so now let us write down a VHDL program for simple half adder. So we know that a half adder has two outputs, sum and carry, and here sum is expressed as A XOR B, whereas carry is expressed as A and B. So we have written down a simple Boolean equation for sum as well as a simple Boolean equation for carry. So since Boolean equations are here, so we can say that this is a data flow style of modeling. Let me put down and comment data flow modeling. What if we want to write down the architecture using behavioral style of modeling? What we will do? We will say I am going to write down a scratch program, not exact syntax check program. So for behavioral modeling, we will say that if A is equal to 0 and B equal to 0, then sum is assigned as 0 semicolon, carry is assigned as 0. Okay, else if we are going to write down all four conditions over here, else if okay, so whenever A is 0 and B is 1, we know that sum will be 1, carry will remain 0. Then if A is 1, B is 0, again sum is 1, carry will remain 0. If both A and B are 1, then sum is 0. Then sum is 0, but carry becomes 1. And after that, we will end our if statement. So this is a kind of modeling. These are the kind of statements we are going to use in behavioral modeling. So we will for now stick to the simple program. So this is a half adder program, VHDL program, which has an extension of VHD. Okay, here you can represent, you can see it is a file ha.vhd, and the asterisk over here represents you haven't saved your file. You haven't saved your file. So as soon as we save our file, the asterisk is gone. Okay, asterisk is gone. Now the next thing, we are going to perform few of the operations. The first operation is check syntax. Double click on the check syntax. It will perform the grammatical check for the design, and if green tick comes in, so everything is fine. Next is synthesize your program. Now this program is going to be converted into equivalent digital circuit or digital hardware, and after performing the synthesis process, we can view the RTL schematic. Okay, what do you mean by RTL schematic? RTL refers to register transfer logic. Register transfer logic. Okay, so let us double click on, let us double click on view RTL schematic. Click on OK. So this is our entity. Entity has input A and B and has outputs carry and sum. Double click on this entity. You will have your design. Okay, and you do have the complete design expressed as the implementation using basic logic gates. What are different logic gates? We do have different logic gates: AND gate, NOT gate, OR gate, NAND, NOR, XOR, XNOR. Okay, total 7 logic gates. How many logic gates? Total 7 logic gates. So your complete design will be implemented using those simplified logic gates. Let us go back to our own program, original program. Now the next step is writing down the test bench. So right click on your file name, click on new source. We want to create a test bench, and that too VHDL test bench. Let us name this test bench as test 1. Okay, then click on next, next, and finish. This is going to open our VHDL editor once again, and this time this VHDL editor will give us space to write down the test inputs. After writing down test inputs, we can simulate the design. Lots of things once again to be noticed over here. First thing, your library and packages. Okay, very important thing over here, your entity is blank. In case of your actual design, your entity is having the port list, but in case of your test bench, the entity is blank. Important thing. Okay, next, architecture of your blank entity. The blank entity has a name, test 1. In this part, we have declared a component, and this component is nothing but your actual design. Okay, you can see a component half adder which has input A, B, output sum, carry, and the component declaration has ended. Next, we have declared some of the signals who share the same name as that of the inputs of the component A and B. Both of them are of std underscore logic type, and both of them are initialized to 0. Then we have declared two signals referring to the output sum and carry. Both of them are of type std underscore logic, but they are not initialized. But they are not initialized. Why they are not initialized? The signals A and B were initialized to logic 0, but sum and carry are not initialized because both of them are output. You can initialize the input to a certain value, but output value depends on your processing. So we can never initialize the output signals. Moving on to next part of the test bench. Okay. Now, since our design is a combinational design, Okay, when we talk about digital design is either combinational logic, where we do have gates, mux, demux, am I right? You do have encoder, decoder, these kind of devices. And the second type is sequential logic. Sequential logic. What do you mean by sequential logic? Everything, the process inside inside the logic or circuit happens sequentially. The components which are used are flip-flops. Sequential logic may do have gates, muxes, demux, and etc. But flip-flops are mandatory. Flip-flops are latches, whatever it may be. Okay. And the sequential logic once again is divided into synchronous and asynchronous design. What exactly this refers to? In synchronous design, all flip-flop elements share same clock signal. Means what? All components, all elements are triggered at the same time. Whereas in case of asynchronous, the flip-flop elements has different clock signals. When you were dealing with counters, and that to asynchronous counter, you may recall that the output of first flip-flop is connected to the clock of next flip-flop. Okay, if probably you remember this asynchronous design, this kind of arrangement. Okay, so coming back to our program. So since ours is a combinational design, we do not require any clock signal, we can delete it. Okay, then we do have instantiation of the unit under test, that is our component. So UUT, that means unit under test. Our design has a name HA. Its port mapping is done. Means what? The ports of the components are connected somewhere. So where the port of our component A is connected to signal A, the port of component B is connected to signal B, the port sum is connected to signal sum, the port carry is connected to signal carry. Okay, then once again we do not require any clock signal over here. So now we have completed our component instantiation. Now we want to apply the stimulus, we want to apply the input. So first thing, hold reset state for 100 nanosecond, wait for 100 nanosecond. Fine, we don't require any clock period. Okay, now after that insert stimulus over here. So what we want to have, our input A to be forced to a value 0 and input B to be forced to a value 0. Okay, then we will wait, let us say wait for 100 nanosecond. We will wait for 100 nanoseconds so that we can observe the output. Let us give few more conditions over here. Let us copy paste the inputs. So first condition was A equal to 0, B is equal to 0, second is A is equal to 0, B is equal to 1, third is A equal to 1, B is equal to 0, and the fourth one is A equal to 1 and B equal to 1. Fine. So we have given only this part of the test bench. Do remember, writing down a test bench in this Xilinx environment is way easier compared to writing down a test bench on the paper. Okay, if you have observed, we haven't written anything but only the input part. So writing down test bench is easier. Save your file. This test bench will be available in this part of your window. Let us save, and as soon as we save our file, we will have our test bench added inside the project. Now let us click on simulation. We do have a test file. Okay, and let us double click on simulate behavioral model. So it is going to check the conditions, given conditions, and it will apply those given conditions to the design file. And let us see whether we do have the output as we are expecting for half adder. Let me click on zoom to full view. Let us put a cursor over here. Here, the input A is 0, the input B is 1, therefore sum is 1, carry is 0. If we put our cursor over here, the input A is 1, B is 1, therefore sum is 0 and a carry is 1. So with reference to the simulation result, we can say that fine, our design is working as our expectation. Now, next part is writing down your UCF file. Go back to implementation. Okay. Now for writing down UCF file, you need to have the manual for your kit. I can give you understanding of UCF in this session since I don't have the manual right now, but let me give you the understanding. Now on your kit, if this is your kit, if this is your kit, on this kit we do have our device, might be FPGA, might be CPLD. This device is connected to some of the peripherals. Let us say we do have one LED over here, we do have another LED over here. Okay, these two LEDs, then we do have a switch, a bank of switches. Okay, now all these components, we have taken a very small example, all these components are connected to your device. Am I right? Let us say this LED is connected to this pin, this LED is connected to this pin, this switch is connected to some another pin of the device, and this switch is also connected to some different pin of the device. Now let us say our entity, our entity, okay, has input A and has input B. It has sum and carry as the output. We need to apply the input through switches. Apply input through switches, whereas observe your output on LEDs. Got my point? So we can apply input A and B 0 0 1 0 1 0 1 through the switches, and accordingly we can observe the sum and carry status on the LEDs. For that purpose, this input A, for this input A, let us say we are going to use this switch. This switch, we are assuming that this is my input A, and this switch we are assuming that this is my input B. Similarly, let us assume this LED represents the output sum, whereas this LED represents the output carry. Okay, I need to configure these things. I need to configure these things, or we will say that we have to put some constraints according to the user. Okay, some constraint has to be put down according to user through a file. So we do have user constraint file, that is UCF file. So what this UCF file will have? we have net A, which will be this switch, and this switch is connected to, let us say, pin number 3. This switch, if is connected to pin number 7. So we need to give a constraint that net A is pin number 3 of the device. Why pin number 3? Because we assume that this switch is our input A and this switch is connected to pin number 3. Similarly, net B. Okay, net B is this switch. This switch is connected to pin 7. So whatever input appears at P7 is our input B. So consider P7, pin number 7 as our input B. Similarly, net sum. Let us give some numbers to these pins of the FPGA. Let us say this is 31. Let us say this is 76. So sum is pin number 31 and the carry is going to be our pin number 76 of FPGA device. Now once we are going to save this UCF file, so VHDL file, okay, VHDL file plus UCF file, these two files will be blended together so that we can generate the programming file or configuration file or configuration file. After this, after creating .bit or .z file, we are going to download these files, these configuration files into your device by using JTAG cable. By using JTAG cable. What is this JTAG? This is Joint Test Action Group. A group whose name was Joint Test Action Group developed an protocol so that these configuration files can be downloaded into your devices. So with understanding of UCF file, how exactly we give name and the corresponding pin numbers of the device, we can combine this UCF file along with the actual logic file. Okay. So this is and flow. This is a flow for implementation of any project in Xilinx ISE environment, integrated simulation environment. Okay. Now few of the things which can be asked for Viva. Let me put down those things somewhere. So Viva questions. Okay. If you are using if we are considering VHDL, yes, a question can be asked as 9 valued logic. Okay, why it is called as standard logic. Okay, or you can be asked as what do you mean by std underscore logic underscore vector. This means this one is single bit logic, single bit logic, whereas this one is a bus, multiple bits. Okay, maybe 2 down to 0, maybe 3 down to 0, and so on. Okay, you have to give the names of 9 valued logic. So those names are, you do have U, X, 0, 1, Z, W, L, H, and don't care. Okay, then you can be asked for VHDL styles of modeling. In between, let me give you the full form for VHDL as well. The full form for VHDL is is VHSI CHDL. You know about HDL. HDL stands for hardware description language. Okay. What is VHSIC? Very high speed integrated circuit. Okay. VHSIC HDL. Then we can be asked for VHDL styles of modeling. Then synchronous and asynchronous reset in VHDL. What exactly this means? Let me give you a simple VHDL program for that. Let us go to logic. Fine. I am going to give you just insight, not the actual code once again. But if we are going to have synchronous reset, okay, so let us say we are going to have a synchronous reset. How we can write down? If we do have a clock signal and there is an event on the clock and our clock is becoming 1, okay, then something going to happen. Something is going to happen. So first thing, let me check if there is a clock. Fine. And this clock represents, this is an rising age. Rising age of clock. Okay. We are going to check if reset equal to 1. Sorry. Reset equal to 1. Then something is going to happen. And if what is going to happen? If reset is equal to 1, let us say we do have an output Q. This Q will be assigned as 0. Reset. Output will be reset. Okay. Else, let us say we do have an input A. Okay. Your input A will be transferred to output. Okay. What is happening over here? In this piece of program, first we are checking for the clock signal. Okay. After checking clock signal, we are checking the status for reset signal. Okay. And after checking the reset status for reset signal, we are performing the action. So first clock, then reset signal. So this reset will be checked only after the availability of the clock. So reset is synchronous to the clock. If there is clock, then and then only reset will come into picture. What if we want to write down asynchronous reset condition? So asynchronous reset, let me put down in this way. Okay, asynchronous. This time, observe what are the changes. If reset equal to 1, then something is going to happen. Okay, what is going to happen? If reset is equal to 1, then Q is assigned as 0. Else if clock is equal to, sorry, clock tick event and clock equal to 1, then Q is assigned as A. Your input A will be available at the output. We are going to end this statement. So what is happening over here in case of asynchronous reset? So first thing, we have checked for the status of reset signal, and if reset is 1, we have made our output Q as 0. Okay, irrespective of clock, we are not checking for clock. Now if reset is not 1, okay, else if reset is not 1, then check for clock signal. And whenever we do have the rising edge of the clock, there is an event on the clock and your clock is becoming at logic 1, clock equal to 1, then we are going to process the signal and we are going to perform the actions written down into the statements. Okay, so in this piece of program, reset is checked independently. Accordingly, output can be defined. And if reset is 0, then clock signal will be observed and actions will be taken. So this is a difference between synchronous and asynchronous statements. Okay. Moving on to next type of questions, synchronous, asynchronous, reset. Then you may be asked to write down the piece of programs for different flip-flops, maybe RS flip-flop, maybe JK flip-flop. Usually D flip-flop or T flip-flop VHDL code is asked. Okay, D flip-flop and T flip-flop. Next, regarding VHDL, whichever experiment you do have, maybe a 4-bit ALU, or you may have FIFO or LCD interfacing. Okay, you may have mod n counters. Depending upon which type of program, which experiment you have in the examination, maybe universal shift registers. Okay, the statements used inside these programs can be asked as Viva. Okay, can be asked into the Viva. Next part, uh, what I will say, after completing VHDL part of the Viva questions, you may be asked for basic definitions. Okay, what is difference between flip-flop and latch? Okay, you may be asked to justify the simulation you have observed after implementation of VHDL program. You may be asked for what do you mean by check syntax, what do you mean by synthesis, what do you mean by simulation, what are types of simulation, what do you mean by implementation. Okay, you may be given some different piece of program to write down a VHDL statement for them. Then VLSI design flow. VLSI design flow. You may be asked about the architectures for FPGA and CPLD. Okay, FPGA and CPLD. You may be asked for that. So in total, there is lots of variety in the Viva questions for VHDL part of the um, examination. Then, if at all everything goes fine, you can be asked the question based on application specific integrated circuits, application specific integrated circuits. This is from unit number 5. Okay, then you can be asked the question based on unit number 6, that is related to testability and JTAG. Okay, testability, and JTAG. So writing down VHDL program in ISC environment, going up to the final Viva. This was an uh, insight insight session for the complete flow and what to write down and what not to write down, and what will be the probable questions, for VHDL part of your experimentation, VHDL part for lab practice to examination. So with this say, I will take a leave and end this live session. I wish all the best to everyone for your examination. Thank you very much.